Hello everyone, I'm back and welcome to the presentation of RSR-NF neural field regularization by static restoration priors for dynamic imaging. Although the proposed method is applicable to different dynamic imaging problems, the focus is on dynamic tomography. The dynamic tomography addresses the recovery of a time-varying object from its projections acquired sequentially at specific times. The problem arises in many different fields. Since the object evolves in time and too few projections are required at any time instant, only one in the extreme case, they are insufficient to reconstruct the object at any time, making the problem severely opposed. The acquired data are the set of projections G obtained with uniform time sequential sampling using the radon transform. If the object was static, it could be reconstructed using filtered back projection. However, inconsistent time sequential projections lead to severe artifacts. To address the challenging ill-posed problem in dynamic tomography, a common approach has been to represent a dynamic object using a reduced number of degrees of freedom. We highlight some of those methods that are most relevant to our work. Overall, the novel RSR-NF framework brings together the restoration network pretraining on static slices of similar objects and the inference stage where the object is recovered from its undersampled time sequential measurements. Thanks to the static supervised training, the restoration network steps are agnostic to the specific motion type. The following points motivate our work. The ground truth dynamic object data for supervised learning is either non-existent or very scarce. Using more accurate spatial priors for the dynamic imaging inverse problem leads to improved reconstructions. Also, existing methods are not easily scalable. Despite the reduction in the memory requirements compared to full object representation, low-rank PSM-based model number of parameters also directly scale with object resolution. Plus, the hard constraint low-rank prior may not be sufficiently accurate for highly dynamic objects. Existing neural field-based methods mostly rely on motion field estimation and suffer from similar limitations. Neural fields are resolution-free and coordinate-based continuous representation models using deep neural networks. Given a coordinate as input, they compute the output features of an object. A neural field representation is particularly effective in dynamic imaging problems since it's essentially resolution-free and the number of parameters to represent the object do not scale with the spatio-temporal resolution. To represent the complete dynamic object, we use a standard neural field where the temporal coordinate is also added to the input. The neural field has an MLP architecture preceded by fixed Fourier positional encodings to mitigate spectral bias. A key component of our work is incorporating spatial priors to neural field representation. The proposed method uses the regularization-by-Denoising framework. Where is a recovery method using an image denoiser in the following regularizer role. Under certain assumptions, it satisfies the simple gradient rule. However, its performance is limited by the denoising pretraining task. The replacement of the denoiser in red by a restoration operator is motivated by recent work that used pretrained restoration models as effective priors for unseen inverse problems, performing on par or better than even diffusion model-based denoisers in red. In the absence of ground truth dynamic data, we pretrain a restoration operator on static slices of different objects using a randomized Gaussian blur kernel as the degradation operator. Our proposed variational formulation to estimate the dynamic object is composed of a data fidelity term using neural field with the radon transform operator, a temporal regularizer as the finite difference approximation to second-order derivative in time, and the static restoration prior spatial regularizer. A major problem with the naive formulation is that it does not allow efficient propagation of the updates on neural field parameters through the deep restoration operator. To tackle this, we perform a variable splitting and apply the spatial regularizer on the full representation. We propose an efficient ADMM algorithm with a single-step fixed-point iteration update for the full object representation. Overall, the novel RSR-NF framework brings together the restoration network pretraining on static slices of similar objects and the inference stage where the object is recovered from its undersampled time sequential measurements. Thanks to the static supervised training, the restoration network steps are agnostic to the specific motion type. In our experiments, we report accuracies with respect to the ground truth object at each time for the two experimented objects. A bit reversed weave-angle scheme is used for all scenarios and methods. RSR-NF is compared with a recent low-rank PSM alternative with pre-learned denoiser prior and TD-DIP, a recent deep image prior-based technique. RSR-NF reconstructions with learned static spatial priors have considerably improved metrics over the ablated version with only temporal regularization and also over other comparison benchmarks. For the walnut dataset, as also highlighted by zoomed-in regions on slices at different times and an arrow on the respective ground truth spatio-temporal slices, RSR-NF has higher temporal resolution, improves recovery of high-frequency features and uniform density regions, and outperforms the comparison benchmarks. Similar results are obtained for the compressed polymer dataset. To the best of our knowledge, RSR-NF is the first neural field-based dynamic imaging method with pre-learned spatial priors. The proposed efficient ADMM algorithm for optimization avoids costly backpropagation through the deep regularizer for neural field updates. Reconstructions show improved accuracies for RSR-NF compared to 3 different benchmarks. Also, the method is applicable to other dynamic imaging scenarios with scarce ground truth spatial temporal data. Here are the references.